Hello. Today I'm going to be showing you how to create a .jb sample file using Sample Creator, how to swap out materials, how to create a brand new design from scratch. We'll be making a MOS2 microcavity sample, how to make a picture of that sample, the basics of how to run a simulation on that sample for reflectivity and transmission, things like that, how to get the electric field from my reflectivity simulations, and how to make pictures of the sample with the electric field transposed on top of them. And lastly, in that area, we'll talk about how to make 2D images for reflectivity, which are going to be angle resolved versus wavelength resolved images. And then lastly, I'll go into a little bit about what the JB sample file is and how to use reflectivity GUI to modify certain properties of that sample and how that gets saved into the file. So first off, in a prior video, you should have learned how to download and install the toolbox that I've made available online. That toolbox comes with a demonstrations folder, so we're going to go ahead and find that folder. So you go to Manage Add-ons. There's my TMM Reflectivity Simulator. We just go ahead and click Open Folder. And let's go ahead and close this. Okay. And, I have some files left in here. I'm going to go ahead and delete them before we start. Okay, so a .jb sample file is the basic way that my software encodes a sample that you've designed. So we're going to first talk about how to design them. And there's two ways you could really go about this. One is if somebody already grew a sample for you, like Dr. Pfeiffer from Princeton, who I'm going to show one of his growth sheets here. Or the second is designing a new sample from scratch. First, we're going to talk about what to do, how to make a sample when you already have the design. So here is a growth sheet from him showing which layers were grown, what materials, how many of each one. You can see here this is 40 repetitions of these layers here. And you've got like aluminum arsenide, gallium arsenide, and aluminum gallium arsenide. So how do we go about putting this into the computer so that we can run simulations on it? We start by opening up Sample Creator, and I'm going to throw it over to the right half of the screen, and we'll put his growth sheet on the left half. Okay, now we won't go through and do all of this because it's a little bit tedious, but we'll do the first bit. So the first thing he grew for us was 7,000 angstroms of gallium arsenide. Now that's actually grown on top of a substrate wafer already. So really, you could start by selecting gallium arsenide and putting down, well, probably about a millimeter. So let's see, 1 nanometer, 10, 100, 1 micron, 10, 100, a millimeter. That would be 1 millimeter of gallium arsenide. I'm not going to, well, all right, we'll put that in. So there's our substrate. And then next, on top of that, he grew 7,000 angstroms, which is 700 nanometers. Make sure you realize that Sample Creator works in nanometers. So we're going to convert that. You can add that on top, and as you probably imagine, it doesn't really influence much. And now these two layers are so much thicker than all the other layers that if we try to plot things on top of them, they're just going to dominate the scale here. So what I'm going to do is I'm going to set it to scale down the first and second layer by, a couple orders of magnitude. And now when I add things in, it'll actually be visible, and you'll see that in a little bit. The next layer he grew for us was 69 nanometers of aluminum arsenide. We'll put all those decimal places in there. Select aluminum arsenide. And now this one is repeated 40 times. So instead of adding it to the sample, I'm going to add it to the multi-layer. And you'll see how we use that in a moment. Next up is 3.083 of gallium arsenide. Again, add it to the multi-layer. And last is AlGas. Now, I have it in here as gallium aluminum arsenide because that was how his notation used to be. But he swapped it with his newer machine, I believe. So I still have the old style function written in there. But yeah, should switch the two letters to make it more accurate with how chemists would write this. Next up, 56.234, add that. And now we're going to repeat this thing 40 times. And there you go. And then it's just methodically marching through this spreadsheet, adding everything in. You might have to periodically clear the multi-layer. So you've got the clear multi-layer. You can also just remove one layer. You can permute it. You can flip it. Obviously with two, they're the same action. And you can clear it, and then you go on to your next material. Now, we're not going to do all of that right here because I've already done it. So in general, that is the preferred method, is just to find a pre-existing sample and just scale up its thickness to match the new sample. So if you want to do things like that, you can click, well, you'd actually do something like that in Reflectivity GUI, but I'll just show you. You can load pre-existing samples, and if you need to add something on top of it, so for example, maybe this one for some reason has a substrate up on top, you can add it in there, and you can modify previously existing ones, and then you can save it. You know, modified P6, whatever. I'm not going to save it here, but you see. Okay. So with this sample file that's already done here, I'm going to show you another thing. So first off, I guess I should mention what is a .jb sample. It's literally just a .mat file, but saved under a different name. And I have a open JB sample function that's stored inside one of the folders from when you installed my toolbox here. And you can see the way you load this thing is you just literally put the -mat thing into the load command. So it's exactly the same as a mat file. It's just a slightly different extension to separate it out from other mat files you might have. So now let's take a look at this structure. And the way this structure is made is the bottom layer is the first layer grown, so it's the bottom layer. So here's that 728 gallium arsenide layer that he grew first. And then you can see all the other stuff in here. And you might notice a special function, which is the gallium arsenide quantum wells. So this is the index of gallium arsenide, but with the effect of excitons, and the excitons have an energy shifted to be about where they should be for our thickness of quantum wells, which are 7 nanometers. But it turns out this is kind of a difficult function to work with for a few reasons, but let's just say we want to swap it out. So how can we swap out all these layers? Easily. Well, you go to Sample Analyzer, and you just go ahead and click or choose Change Sample Layer Materials. Select the sample you want to work with. Now, I can either select certain layers I want to play with, or all layers of a given material. So we're going to do all layers that are quantum wells, and we're going to replace it with simple gallium arsenide quantum well, or maybe one of my other 3 variants of this index. These are different functions that represent the optical index of the materials you're working with. So go ahead and hit that, and now we're asked how we would like to save this. So I'm going to save it as that original name and then simple quantum well. Okay. Now, just a second. Okay, so that's how you can take a pre-existing file and modify what materials are in it. But also, how can we design a sample from scratch? So Sample Creator actually has some tools built in that are going to help us do this. So we're going to go ahead and make a microcavity sample for MOS2 monolayer flakes, which are TMD materials. And we're going to start with the common one, which is a silicon wafer. And we probably want a millimeter of that, so 1 nanometer, 10, 100, 1 micron, 10, 100, 1 millimeter. Add it in. And usually these wafers, when you get them, they've got like 45 nanometers of silicon dioxide on top. And then from here, we're ready to start the growth procedure. And typically, CVD stuff you're probably going to be working with silicon dioxide, silicon nitride. So I'll show you. We'll make a microcavity out of silicon dioxide, silicon nitride. So we'll go ahead and go with silicon nitride first. But before we do that, we want to go ahead and turn on the tools that are going to make this easier for us. You could do all of this calculations by hand, but this will save you a bit of time. So you click autofill thickness. And I know that MOS2 monolayers are at about 670. That's where the exciton is, at least the exciton of lowest energy. And then I know I'm going to be working at room temperature, and I want to work at normal incidence. And if you recall, the way you make a DBR, distributed Bragg reflector, is that you make each layer of it 0.25 wavelengths. Now that's wavelengths in the material. So really it's 670 divided by 4 times n, where n is evaluated at 670 and 300 degrees and 0 angle if you're going to have an angle-dependent index of refraction. So now we hit OK, and now it'll automatically populate this with the relevant number for you when you swap materials. So we'll go ahead and go to silicon nitride, add it to the multilayer, silicon dioxide, add it to the multilayer. Let's add 10 of these onto our structure that we're starting with here on the left. And now the top DBR is going to be the bottom DBR just flipped, so we can use the flip multi. And before we put that in, though, we got to put our active medium, so we're going to go to simple MOS2 monolayer, or if you want, simple gallium arsenide quantum well. They are actually the same function, it's just they have different names just to help people realize what's going on there. And this number that it auto-populated now is not the relevant number for us because we're dealing with monolayers of MOS2. We're not using it to make a DBR. Typically the monolayer is 50 angstroms, so we'll put 0.5, or tell you what, we'll just put 1 nanometer, add it to the multi, or sorry, not to the multi. I'll remove that from the multi-layer, add it to the sample, and then add the multi-layer on top. And now we're ready to save that as a MOS2 microcavity. Okay, so now we'd like to see if this is a good design. Does it work? Does it do what we want? So we go into reflectivity GUI. Oh, and I just realized I should have mentioned I started out inside of this folder called Reflectivity Simulator, which is in the folder from our toolbox. I should show you how to get there. If you go to Manage Add-ons, and then you click Open Folder on my thing, it'll bring you here. And then there you go. Okay, so now we go ahead and open up Reflectivity GUI. And we're going to start by loading in the sample that we just created, MOS2 microcavity. And now we can start going through some of this stuff here. So EXP scalar and shift, you're not going to need to work with that for a while. Angle, we're going to simulate at 0 degrees of normal incidence. We're going to run this simulation at 300 Kelvin, which is room temperature. And then what wavelengths do we want to work with? You can put 3 in here. I sort of put this in so you could like zoom in on regions of interest easily. But actually, in practice, I find I don't even really like it. I like to just work with 1 usually. And so I'm going to put 600 to 800. Okay, so we've got a microcavity for sure. That's obviously a cavity mode in the center, and that's a stop band. That's the characteristic flat stop band we'd expect. And maybe we actually want to go ahead and put this down to 550 to get a little bit more visible. There we go. Okay. So that's the basics of how to run the simulation. I clicked this button here, Update Reflectivity, to run it. And you can see I can swap between various calculated quantities. So I've got reflectivity, I've got transmission. Now for transmission, you might have to zoom in a bit. because maybe it's not transmitting all that well. Oh, or maybe it's not transmitting at all. It's probably not transmitting at all because we put an entire millimeter of silicon on the bottom, and that's kind of absorbing in this range. But what if we looked at absorption instead? There, we see maximal absorption at the cavity mode, which makes sense. You could also look at P polarized or TM reflectivity. Of course, at 0 degrees, they're the same. And then you can also look at unpolarized, which is just an average of the two, but again, they're the same, so the average is the same as all of them. And then we have some elliptical quantities, or sorry, ellipsometry quantities you might be interested in, like Tm over Te for, reflectivity, transmission, and absorption. Of course, at 0 degrees, it's all 1 because they're all the same. But if you were to go out to, say, the Brewster angle up at maybe 60 degrees, you would see significant variation. Okay. So now that we know how to run a basic simulation to get our reflectivity, how can we get a nice picture of this sample? Well, if you click this button, Picture of Modified Sample, and don't worry about that word modified, we'll talk about that in a little bit, it'll pop up the E-field GUI, and you can then go ahead and zoom in and get a feel for what this thing looks like. And if you want to change it, so these optical indices have to be evaluated at some values because that's what this plot is. On the vertical axis is optical index, on the horizontal axis is real space positioning. This one I evaluated at 0 Kelvin by default, but we're going to work at room temperature. Now, if I didn't bother to program temperature dependence into these functions, nothing will change. But I also know that the wavelength of interest for MOS2 samples is about 670, so we'll change it to that. And then we just tell it to redraw that. Okay. And if you wanted to save this figure, you can click this pop-out button here, click on the figure, or the axis, and now you can go ahead and save that, do whatever you need to do with it. It's just a regular figure at this point. Okay, now I've now shown you how to run a basic simulation, but now we want to do a simulation with electric field. And actually, I have a lot more than just electric field in here. You should think of this as like the premium version of this code, all right? This is when we're going to turn on some of the more computationally intensive stuff. So you don't normally leave this on all the time, but we're going to go ahead and click Integrate Electric Field. And what that's asking us is it's going to ask which layers do we want to do a real space integral of the E-field over. Now that's just one quantity it's going to calculate is an integrated E-field. There's a lot of other ones that you maybe don't even need to worry about, but it all just does it all in one. So I'm going to select the entire microcavity here. Actually, we'll just select the monolayer. And now for the purposes of real space integration, it's going to break it up into n layers. Each layer that you selected to integrate, it'll break it up into however many layers you type here. 20 is usually a good amount. All right, so now the simulation is primed for E-field integration, and now if I hit update, you'll see it's a little bit slower, but not terrible. And now we've got this black curve added to the bottom, which is the TEE2D total 2. Now, what does that all mean? It's the transverse electric, so S-polarized electric field, integrated over the space that you've told me to integrate over. And it's X and Y and Z components squared, added together, and we didn't bother to take the square root of that. So it's E-field squared. Now, you can swap what quantities get displayed here. So, for example, you might want to look at magnetic field, which I've tried to scale to be on about the same size, but it's difficult. So it's really a plot of C times the magnetic field. Or you might want to look at the total energy in the region you told me to integrate. You could also look at how much energy is being dissipated in that region. And now, because this is such a small amount, you might want to scale this thing up. So I could maybe shift it up a little bit. And then I could also increase its scaling. And you can see that they line up quite well with one another. Okay, and an interesting thing is oftentimes the energy dissipated or the E field, these quantities kind of help us find things sometimes. So we can see there's a second bump here at 660 and then another one at 630. What might that be? Well, we'll talk about that in a little bit. But for now, just know that the integrated electric field or this dissipation quantity can help find stuff. So the next thing I want to know is how do I get this electric field plotted on top of the sample? Because that's a really helpful graph to have. Well, let's take a look. Like I said, we've got the cavity mode at 675, and we've got the secondary mode, whatever it is, at 660. So now let's go back to our E-field GUI. Let's zoom in. And now you can see this magenta curve, which is the E-field at that location. Now, it's time averaged, of course, because our E-field sometimes is 0, sometimes it's maximal, so you've got to average it. And this is the total electric field squared, so in-plane and out-of-plane electric field squared. And right now we're at 550, which is our lowest wavelength. Let's go take a look at 675. So I'll tell it to go to 675. It'll find the I value that's closest to that. And I could always step along it if I wanted to. And you see it doesn't change much because it's a fairly long, or sorry, a fairly large line width here. So because I'm using a fairly small step size, each step in my index doesn't change a whole lot. Okay, and then I can also look at different quantities. So right now this is the electric field, and then that's the magnetic field. And if I wanted to, I can shift it up a little bit, maybe something like that. I could scale it a little bit. Maybe the E field looks nicer. And if I want, I could add the E field and the B field squared together. It's really C times the B field, of course. And there's my total energy. Or I could look at the total dissipation. Where's all my dissipation occurring? And I can see most of my largest location of dissipation is in the monolayer. Now this is dissipation divided by volume, so that's why it can spike in the monolayer. Of course, the monolayer is so thin that if you just looked at total dissipation, it would be almost 0. What other quantities are in here? Well, you can look at p-polarized or unpolarized quantities as well. One last thing. So this plot, as we have it here, is kind of jagged, right? And that's because the electric field only needs to be calculated at boundaries. Now, dissipation is calculated at is given the value as being at the center of the material, and electric field is at the border. So you can see the electric field is at the border here, and I've only got it evaluated at the borders of these materials. Or dissipation is evaluated at the center, and it's averaged over the entire volume. But if I want to make a nice picture that I could maybe publish or share even just in a PowerPoint presentation or something, this isn't really going to do. So what we do is we go back here, and now we're going to sort of break the integrate E field button. So now what we're going to do is we're going to select all the layers, and we're going to say integrate every one of those layers. And now when it asks us, we're going to say do 20 points per layer. And now what that's going to do is break every layer up into 20 points. Now, of course, this is going to slow down the simulation a little bit, but you only have to do this at the very end of your work when you want to make a nice figure. So it's not too bad. You can see it's working on it. And I made it a pretty long. Yeah, actually, in reality, I probably could have trimmed this down quite a bit to save some time here. I could have gone like 670 to 680. Yeah, actually, I might have maxed out my RAM here, in which case my computer will really start to struggle. Yeah, let's go ahead and control kill this. Control C. Although once it's been sent to the BLAS, it might not be so possible to interrupt it. There we go. We got it out. There. Okay, back over here. Let's go ahead and run it again now without maxing out my RAM. And you can see that one ran a lot smoother. Okay, so now go back to our E-field GUI. We tell it, hey, show me 675.12. That's where my cavity mode was. Show me the E-field. And this could be a little nicer looking if we shifted it up like that. Yeah, that looks pretty nice. And actually maybe even a little vertical pan. Yeah, that looks pretty nice. And that shows people that the E-field's spiking right on top of the monolayers. And then you could use the pop-out function again and, go ahead and change your legend to be whatever, make it a little nicer than this, whatever you got to do. But there you go. That's a nice figure with the E-field plotted on top of it. Okay. And again, I guess I should mention, yeah, you'll get a feel for what's going to cripple your computer and what isn't, because once you start maxing out the RAM, the simulation slows down a lot. So you've got to be careful with how much you use here. So, that's why you've got 3 here to sort of help you out. So you can do broad, fine, and then finest, and that'll help you out a lot. Okay, and then the last thing to mention here is you can actually go ahead and run this simulation at many angles. So if I wanted to now go from 0 to 30 degrees, let's say, for my angle of incidence, I can go ahead and run it. And I just got to be patient with it. Let's see, the last one was 2 seconds. I've just increased it by 15, so now it might be a 30-second integration. So actually, I probably should have cut that down a little bit more. Oh, I guess, yeah, I did leave the integrate E-field on, so that's going to slow things down quite a bit now that I think about it. But okay, it's done anyways. So now if you do a 2D simulation like this, it'll export the final result to Quick Movie GUI. And so you can use your crosshair function here to get profiles. And you see there's a lot of different images it produced. So we can look at the electric field in plane. We can look at the electric field out of plane. We can look at the total E field. So I guess the out of plane electric field was nearly 0 there. We can look at the energy dissipation. And basically what this is it's your cavity mode, and it's showing you the dispersion relation of that cavity mode. We can also just look at regular quantities like the reflectivity. And you see that characteristic dip. And there's also some ellipsometry things still. So just like in the 1D GUI here, where we had all of these and all of these, we have that now in the 2D GUI. And also, we can still look at pictures of the E field. So now we can click Picture of Modified Sample, and we can go ahead and zoom in. And so now we know that if I go to 675, was it? Yeah, 675 at 0 degrees. I get a spike near the center. But what about at 30 degrees? Well, go back to my 2D GUI. Oh, I can see 30 degrees is too far. But at 11 degrees or so, looks like, or that's going to be 12 degrees, we can get away with, we can see the cavity mode at 670. So let's go take a look. 670. There you go. And you can march around in angle if you want. You can march around in wavelength if you want. And there you go. Okay. So next up, we want to talk about how to modify layers and samples in Reflectivity GUI, and how to save that, and what that all looks like. So first thing I'm going to do is I'm going to turn off some of these options that make it a lot slower. So I'm going to turn off this integrate E field, which was splitting every layer up into 20, and I'm going to go down to just 0 degrees. And now we're going to talk about what we can change here. So first off, see if this will work. This will work okay. Do my best to work with just the one monitor here. So first off, I can change which layers are part of the simulation. So if I want, I could go down to n-1, and now you can see I don't have to deal with that substrate anymore. Or if I want, I could go down to like n-10, tell you what, maybe 20, and 21, 22. 22 should do it. 22, and now I just have a DBR on top of a monolayer. So actually I probably should have gone 22 to end, something like that. Yeah, and now I've got, no, I've just got DBR on top. So probably 20. There. And now that's like a DBR with a monolayer on top of it, which is a sample we often have as well. And that's not all I can do, though. I can also change individual layers and thicknesses. So let's go ahead and go back to this. Let's just say I wanted to make silicon much smaller amount. So basically remove almost all of the substrate. Maybe we did a bromine etch to get rid of that substrate on the bottom. And now you can see, all right, I've got a thinner silicon dioxide substrate. But what else could I do? Well, I could, what if I wanted to tweak the cavity mode? So right now the cavity mode is here. And let's say I wanted to move that cavity mode to 673, about here. Well, what I could do is I could define a specific layers function. I could select just the 3 that make up the cavity mode, these 3 here. And I could give it a name, cavity. And now if I cut that down, cut it down too much, I'm going to use the show prior simulation function here just to help us keep track of the changes. And I'm going to also lock it so that things don't change again. Okay, and so see here, I could play around with this a little bit, move my cavity mode, try to get strong coupling, things like that. I could also just scale the thickness of everything. So for example, every layer of silicon dioxide, maybe I want to make it 10. And now if I look at my picture, there you go. Now it's all 10 times as big. We have some other abilities too here. We don't only have to change thicknesses of layers, we can actually change the thickness of the whole sample. So I'll show you that. Now pay attention here, it's about 5 microns of sample. Now it's about 50 microns of sample. And I can also change the index functions. We have 2 main ways to play with our index function, or the index functions of our materials, which is we can play with these simple modifiers here. So for example, say I just wanted to turn off all dissipation in silicon. So I could go to the imaginary piece of silicon, and I could just say multiply all of the imaginary component of the index of silicon by 0. And maybe that changes things a little bit, but maybe not that much. But maybe I want to try playing with the real part of the index of silicon dioxide. Maybe I want to double it. Let's see what happens. And it does all sorts of crazy stuff. Or maybe just 10%. How does that change things? Maybe just 1%. Probably just shifts things a little bit. So all sorts of stuff you can do there. Now, these index functions, where do they live? Well, if you go to my toolbox and you go to sample simulation and you go to material index library, this is where they live. And any function you add in here will automatically show up in, sample creator and things like that. And I recommend you follow my notation here if you add any of your own. And I'll show you what these functions look like. I always have persistent variables for what you're going to load in. That way you only have to load the file once. The file that you're going to load is saved inside this folder. And you see I have all these different types of materials, some of them under different angular settings, things like that. And then it does an interpolation scheme on it. And it's all vectorized, so if you put in multiple wavelengths, multiple angles, it'll all work. Okay, but some of them are special. These functions that are called simple here, they're actually tunable. So these functions, like this index PMMA, it just loads a file. Usually one that I found off refractiveindex.info or one that somebody took for me using an ellipsometer or what have you. But the simple functions, such as the one we've been using, simple index of MOS2, they behave a little differently. They have a ability to output what inputs they expect if you call them with no input. And I use that in reflectivity to give you tunability. So let's go take a look what that looks like. I can go here and click add variable. And if I use just a regular old index function, nothing happens because there are no variables to tune. But if I do it for a simple function, it gives me variables and it says which variable do you want to tune. And we're just going to go ahead and throw them all in there. And now I can see the parameters and they're exposed directly to me. So let's go ahead and try giving ourselves some room to play here. Okay. Now, what if I took the exciton A and I moved it up to try to be resonant with 672? Okay, so something changed a little bit. Now, you'd have to play with it a bit to get strong coupling. The gallium arsenide sample I've included in the demonstrations folder will show you strong coupling. This sample that we just quickly made here probably won't show it so easily. You usually have to play with the parameters a bit. And just so you can see exactly what I'm doing here, what we can do is right-click, make index plots, and I can select any layer that I want, and I can see what its index looks like in my simulation here. And you can see here my exciton A, my exciton B, and if I want, I could change this. Maybe it's shifted up to 690. And there you go. You see it's shifted out of there, and now it's not even visible on here. And this is what it looked like originally. So that's a convenient way for you to keep track of how you've changed your index. Now, a lot of times you're going to be doing some pretty big projects with these things, and you probably want to save your results, save your position, so you can get back here if you have to maybe shut things down or go home or whatever. So I have two options for that. The one I recommend using the most is the save state for the GUI. So for example, I'll just call this tuned MOS2. And now, because I've saved it, if I close the GUI, I shut down MATLAB, I come back the next day, I can double click on this JB reflfig file, which is just a fig file, but I've given it a slightly different name to help separate it out from the other stuff in your folders here. You just double click on that, my function will take over and open it, and now you've got the GUI. And you're back where you were previously. Everything's the same. Alternatively, after you've done all this work to scale a sample and tune it and probably fit it to some data, you can save the scaled sample using this button. I'll just give it a name. And now let's go take a look at what that looks like. So the original sample, if I double click it, it loads it into the workspace. And we can take a look at its structure. And you've got, the index function that we're linking to for that layer, a string that just helps that's for a human to read, thickness, the units that we're working in, and a color, which is just for plotting purposes. Now, what if I look at the modified one? Now you can see 3 new fields have been added to it. A real scalar for the index. So here I scaled the index of silicon by 1, but the imaginary part of it by 0. And then there's also an external tuning parameters for the materials that accept it. So silicon dioxide doesn't have it, but the simple MOS2 does. You can click here, and these are the numbers we had set. So that's how it saves that data. But normally, I find I don't like saving scaled samples. I prefer to just save the GUI instance most of the time. I find that's more helpful. Okay, I think that covers everything I wanted to cover in this video. How to modify, how to save samples, modifiers, 2D electric field simulations. Yep, that's everything. So there will be more videos on other stuff, but that's it for today.